Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on the MATLAB simulation of control systems. Today we are going to discuss the dynamics and terminal sliding mode control of a two-linked flexible manipulator with non-correlated feedback. So I have a couple of videos related to the sliding mode control for robotic manipulators. I will share the links of those videos in the description of this video. But the difference here is that this time we have a flexible manipulator, so there are some additional dynamics involved in the model of the robotic manipulator. As usual, we will just be looking at the dynamic model of the manipulator and the control implementation. We will not be discussing the paper itself in detail. You are most welcome to download this paper from the appropriate source and study the paper by yourself, and then this video can help you in understanding how to simulate the dynamics and the control discussed in this paper. So the robotic model that we are going to discuss is a two joint model where we have theta 1 angle of the joint 1 and theta 2 angle of the joint 2, and we will also be considering the rates of change of theta 1 and theta 2 in our model M1. This capital M1 and capital M2, these are the masses of the motors. So and then we have the masses of the joints themselves, which is given by the small case M1 and M2. So here is the description. Masses M1, M2, the lengths L1, L2 are the lengths of the joints, the links. And then we have the main model of the robotic manipulator is this one, where MQ is the inertia matrix and C is the Coriolis configurational centrifugal force matrix, and K is the stiffness matrix, tau is the generalized driving force, F is the external disturbance, which is assumed to be bounded in this case. There are some derivations of the dynamic model that is discussed here. We are not going into the derivations of the model in this video. We are just going to use this model that is discussed in the paper and simulate the control systems. Then they have converted this model into an equivalent form by defining the D matrix to be M theta theta, which is like the first block of the M matrix. So M matrix in this case is a 6 by 6 matrix where M theta theta corresponds to the angular rates. So Q theta double dot is the angular accelerations of theta 1 and theta 2, and then delta are the variables that are associated with these coordinates. They call it see here, delta ij is the mode coordinate vector. So mode coordinate vector is also incorporated into the dynamics of the manipulator, and these are four of them: delta 1 1, delta 1 2, delta 2 1, and delta 2 2. So this M delta delta is 4 by 4 square matrix, M theta theta is 2 by 2 square matrix, and M delta theta is the transpose of M theta delta, and these are of appropriate sizes so that the overall M matrix is of 6 cross 6. So there will be like 6 of these variables, 2 variables in the Q theta and 2 variables in the Q 4 variables in the Q delta. Then there is this is the alternate form of the state space equation. X1 dot is equal to x2 and x2 dot is equal to d inverse tau theta plus ft minus h. These are only the dynamics of the theta 1, theta 2 and theta 1 dot and theta 2 dot. The dynamics of q delta, these can be derived from this equation, and then this h is clearly defined in the paper and d is also defined in the paper. And then the details of m theta theta, the full details of this whole M matrix and C matrix and this K matrix, these are given in the appendix. So if you go at the end of the paper, this is the full description of the M matrix, and this is the full description of the components of the C vector, which has 6 components, C1 C2 up to C6, and K is 4 cross 4 matrix. All of its elements are given here because it's a diagonal matrix. And then there is some proof of asymptotic stability, which we are not going into, and also the simulation parameters are given. So the values related to the control gains are given in the paper, and there are some parameters of the system which are also given in the paper. They have also compared this whole thing, the terminal sliding mode control, with the PD control, but I'm just gonna let it be for you. It's very easy to implement PD controller, so I hope you can do it on your own. Just change the equation for tau theta from terminal sliding mode control to this given equation, and it will be done. About terminal sliding mode control that is proposed in this paper, it's a little bit complicated because the control itself, the equation of the control is equation 26, which involves this D matrix, H matrix, which are the matrices from the dynamical equations. Then the second derivative of the desirable trajectories, P double dot, this is some special variable defined in this paper, and then Z1 Z2 are sort of gains, and this S is the sliding surface. So sliding surface is given by here is the sliding surface is equal to Z times E minus P, where E is x minus x E is the basically error and rate of change of error vector. So error is the difference between x1 and x1 desired. So x1 in this case is theta 1 and theta 2, and these are the desirable trajectories for theta 1 and theta 2, which also is equal to x1 is also called q theta, as you can see here in the above dynamics given in the beginning. So this q theta double dot, so q theta is basically, this is q theta, theta 1 and theta 2. So later on it is called x1 in the paper. And then they also give you this P is equal to basically it is P1, P2, P1 dot and P2 dot. It's a vector of size 4 cross 1, and then P1 is calculated through this complicated equation, which is not too much complicated, but it's a long equation which involves the initial values of the error and the initial values of the derivatives and the double derivative of the error, and then there are some coefficients which are calculated here. Then you once you calculate P1, P2, P1 dot, P2 dot, in order to calculate P1 dot you have to take the derivative of P1 from this expression. And now without further ado, I think we should move to writing the code for this paper. So I will keep the paper and the code side by side, and I've already written the code and I've also run the code because this code takes a lot of time to run, so I don't want to run it while making the video because it will take like 1 hour to run. So we first of all we have to write the MATLAB function. Dx is equal to I have given it the name T terminal sliding mode control underscore flexible manipulator. You can give it any name, does not matter. So first you have to write the values of this is the value of the initial condition for theta 1 and theta 2 that we will be using later on. This is the value of capital T. So capital T is this capital T value. It's given in the paper. It's given later on in the simulation numerical simulation section. Then I define delta 1 1 is equal to the fifth variable of the state, delta 1 2 is the sixth state variable, delta 2 1 is the seventh state variable, and delta 2 2 is the eighth state variable. So the first four state variables in my code will be theta 1, theta 2, theta 1 dot, and theta 2 dot, and the next four variables will be the delta 1 1, delta 1 2, delta 2 1, and delta 2 2. And then I define the derivatives of deltas, because these are also going to be used. So delta 1 1 dot is the ninth state variable, delta 1 2 dot is the 10th state variable, delta 2 1 dot is the 11th state variable, and delta 2 2 dot is the 12th state variable. So I have total of 12 state variables in the system, because that's how this system will work. And then we write down the values of L1, L2, M1, M2, EI1, EI2, M1, capital M1 and capital M2, which are given in the paper in this if you go to this table, all of these values are given in this table. And then we start writing the equations that are given here. So in the appendix there is a equation for M11, so we just type the exact same equation, and then we similarly type the exact same equation of M12, which is given here, and then we type the equation of M21 is basically equal to M12, which is M12 is equal to M21, so that's simple. And then we type the equation for M13, and M31 is equal to M13, and similarly M14 is equal to, also all of these equations are given in the paper, so I'm not going to spend much time. You can just type them, and once you have completed all of the equations, then you type the equation for C1. The expression for C1 is very long, but it does not matter. You just type as it is in the MATLAB as it's written here. You just have to be careful not to make mistake. And then you write the expression for C2, C3. All of these are given in the paper. So this expression, this is the expression for C2, C3 we use. So remember that in this X3, so you have to remember the notations that we are using. So D11 is delta 11, D12 is delta 12, D21 is delta 21, and D22 is delta 22, and similarly DD12 is delta dot 1 2, and similarly x1 is theta 1, x2 is theta 2, x3 is theta 1 dot, and x4 is theta 2 dot. So these these notations you have to keep in mind, so that you don't make mistakes. So we keep going in the similar manner. We define C3, C4, C5, and then we also define C6, and then later on we define K1, K11, K12, K22, K33, and so on, which are also given in the paper. And then we define this M matrix to be all of these very similar to what we have here. So this is the configuration of M matrix. So we define the full M matrix, and then we define the K matrix to be the diagonal matrix with entries K11, K22, K33, K44. Then we define M theta theta, M theta delta, M delta theta, and M delta delta. which are given here. So we use the, so if you look at this, so m theta theta is mtt, which is the first 2 cross 2 block of this matrix M. Similarly, m theta delta is first 2 rows and the column number 3 to 6, and similarly m delta delta is column and rows, the last 4 columns and rows of this M matrix. And next we define the D matrix, which is given here. So D is m theta theta minus this whole expression, so we define the D. Similarly, we define C delta and C theta. So C theta is basically the last C theta is the first 2 elements of the C matrix, C1 and C2, and C delta is the last 4 elements of the C matrix, which is C3, 4, 5 and 6. And next we define the H matrix as given in the paper, and also the F, the disturbance, is given to be 0.02. It's also mentioned in the paper in the numerical simulation section. And then we define this x1 desire is sine t and cos t. So desirable trajectory for theta 1 is sine of t, and desirable trajectory for theta 2 is cos of t. We can easily calculate that the derivative of sine t is cos t and derivative of cos t is minus sine t. So x1 desire, the derivative of x1 desire is x1 d underscore d, and the double derivative of x1 desire is x1 d underscore double d. So these are the notations that I have used. You can see here the desirable trajectory, this is the value of disturbance 0.02, which we have defined here. F is equal to 0.02, and similarly, if you go on this side and on the next page, they say that the desirable the initial conditions are 0.4 and 0.6 radians, which are given here. And we use initial conditions. It is unusual to use initial conditions in the function file, because we provide initial condition when we call the ODE45 function for this file. But in this case, these are going to be used in the control equation, so we have to define them here. And then these are the desirable trajectories: sine t for theta 1 and cos t for theta 2, in which we have written here. And then we define the error to be x1 x2 minus the x1 desire, and similarly we define the derivative of error, and we define all the other terms. These are the terms which are going to be used in this p, the calculation of this variable p or function p. So a00, a10 and all of these, and also x10 this is the initial conditions which are going to be used in the, so there are, this is ei, e10, e20. So these are the initial conditions of the errors, and so these are defined by e10. E01 is the initial error in theta 1, E02 is the initial error in theta 2, and similarly ED01 is the initial error in theta dot 1, and ED02 is the initial error in theta dot, and similarly they are double derivatives. They are pretty easy to calculate, because the derivative of the constant is 0, and the derivative of the desirable like sine t with t is equal to 0 is 0, and cos t with t is equal to 0 is 1. So all of these derivatives are the initial values of derivatives are 1, 0 or minus 1, depends. So this minus 1 comes from plugging in t is equal to 0 in minus cos of t. So then you have to define the if condition, because p1 of t is equal to this whole expression if t is less than, if t is between 0 and capital T, otherwise p1 is 0 and p2 is 0 and so on. So we define the whole expression for p1, p2. So these are the constants that are going to be used in the expressions for p1 and p2, and then these are the this is the whole expression for p1. You can see here. So this is the same that is same equation that is written here, and then this is p2 with p2 is with e02 instead of e01. In p1 e01 is used, in p2 e02 is used, and so on. And then similarly we can write p1 dot and p2 dot, because in p1 dot you can see here this constant term, its derivative will be 0. This is multiplied with t, so derivative of t is 1, so this term will come as it is. Here all you have to do is take the derivative of the t in different terms. So derivative of t square will be 2t, and this is a constant, it will come as it is, and so on. So you can calculate p1 dot and p2 dot, and similarly you have to calculate the double derivative as well, p1 double derivative, p2 double derivative, and whenever small t is whenever the time is greater than or equal to capital T, then all of these are 0. Next you define this capital P, which is p1 p2 p1 dot p2 dot. This capital P is used in the sliding surface. You can see here sliding surface is z times e minus capital P. So this is the capital P which is used in the sliding surface. And then this is the S0, S1, sigma 0 and sigma 1, these values, and the value of F, these are given in the paper. These are the constants which are going to be used in the in the control. And then this is z1 and z2, which this z is basically a combination of z1 and z2. So z1 and z2 are also given in the paper. So z is equal to z1 z2. And similarly e is error and the derivative of error, as you can see here. And similarly s is z times e minus p. This is the sliding surface. Then we have PD, the derivative of P in terms of vector p1 dot p2 dot, and p1 double dot and p2 double dot, these are p underscore double t. So these are going to be used in the equation for tau, which is here. So this is the equation for tau, the whole equation from the paper. Here instead of in this equation I have used this, instead of using this z2 transpose s over z2 transpose into s norm, you can replace it with z2 transpose into s divided by this whole thing. So I have used this expression instead of this in the tau equation. So you can see this is the tau equation. And then in the end I define the dynamics. X1 dot is equal to x2, which is x1 is in my case it is theta 1 and theta 2, and that its derivative is theta 3 and theta 1 dot and theta 2 dot. So we keep going in this manner, define the rest of the state space. So x2 dot is the d inverse tau plus f minus h, as is given in this equation. So we have already defined, so this is x2, so x1 dot is equal to x2, which is this equation, and x2 dot is equal to d inverse tau theta plus f minus h. So f is the disturbance, h and d are defined already, tau is the control law which is here. is the long equation of control law. Next we define d1 is the delta 1 dot, which is 4 delta variables: delta 1 1, delta 1 2, delta 2 1 and delta 2 2. We have already defined them to be state variables 9 10 11 and 12. State variables 5 6 7 and 8. So state variable 5 6 7 and 8 are the deltas, and the derivatives of the deltas are state variables 9 10 11 and 12 as are defined here. So these are the derivative of delta 9 10 11 and 12. And then we define the derivative of deltas with this equation, which is given here as I think it's above. So this one, equation number 18. So this is written here, and then we finally complete the file with returning x1 dot, x2 dot, delta dots and delta 1 dots, which are the 4 delta variables, and delta 2 dots, which are the derivatives of the 4 delta variables. And then in order to run this file, we have to call ODE45 function, and this is how we call them. We run it for 10 seconds, and we give initial conditions of theta 1 and theta 2 as 0.4 and 0.6 radians as given in the paper, and also defined in the function here as well. So we have defined the initial condition here and used them in control equation, but we have to give them to ODE45 function as well. So all other initial conditions are 0, and we give okay, in order to calculate the control law, because we have to plot the control law as well, what we do is that you just copy this whole code up to the point where you define the equation of tau. So this is the point up to which we define the equation of tau. You copy all this code and paste it here in a new file. So I have pasted it in a new file. So this is the code, the same code that is used here and we have discussed already, but only up to the value point where we calculate tau. And we call it a new function, tsmc underscore control calculation, and it takes in the input t and x. So here for all the values of all the points in time, you calculate the tau vector using this control using this function tsmc control calculation, which is created by copying the code from this file. Okay, so if you okay, I hope that you understood what I just said, so I will just repeat it. This function, control calculation function, is just from the line 2 to all the way to the end. This is just exact copy paste from this original dynamics and control function that we have just discussed in the whole video. You copy this all the way up to the line where you define the tau and paste it into the new m file here, and call that m file a different function name, the calculation of control, and then you can call that m file to calculate. So these are the values of time and state variables which are calculated after integration of the dynamics. So you plug in those time and state variable values to calculate the control. This is sort of like a reverse engineering for calculation of the control signal. Then you can plot the theta 1 and the desirable trajectory of theta 1, and theta 2 and the desirable trajectory of theta 2, and in figure 3 you can basically plot the control function. I have already done that, because if you run this file it will take about 1 hour to run, because the dynamics are quite complicated and MATLAB struggles in solving the dynamics. So if you compare these results with this is the result which is given in the paper regarding link 1. So it's not exactly the same, but it's a little bit of different. Maybe there is something different, because there is one thing different. I used instead of using this, I used this expression, so maybe this made some difference, or maybe there is a slight error in my code, or I don't know what's the reason, but there is a difference here. And similarly, there is this is the plot for theta 2, and if you look at the plot for theta 2 in the paper, I think it is this one, the joint link 2 angle. And if you look at that, so this is also not exactly the same, but the tracking is there. And finally, if you look at the control signal, the control signal that is given in the plotted in the paper, it varies from about plus 200 to minus 200, whereas if you look at the control that I have plotted, it's of similar shape, but it varies between plus 40 and minus 40. So there is clearly some difference. And also I just want to point it out that there is something which is quite different in my findings, that is different from this paper, that if I zoom this out, because I have zoomed this code in quite a lot. So if I zoom this out, yeah, and then zoom in the initial I have to wait, because this is a very heavy data, so MATLAB is struggling to, there is a lag in the computer due to the nature of the data, because the data points are too many. So I have to wait a little bit maybe. And I zoom here in the initial part, and you can see here that for the initial few milliseconds, the value of the torque is quite high. So this is, the value of the torque tau 1 goes from 900 Newton meter, and it comes down within 10 milliseconds. So the first 10 milliseconds, the value of the torque is quite high, which is not depicted in the paper, but it is evident in my simulations. You can recreate the code that I have written. So this is I hope that it will so you can take a screenshot of this part of the video, then second screenshot of this part of the video. So these are the two screenshots, give you almost 70% of the code, and then the remaining code you take screenshot here and you take screenshot here. So these 4 screenshots will give you the whole code, and you can type it. And I have also shown you how I have written it, so you can write it without the screenshots as well. And then this code is easy, and the other code is just a copy paste of the previous one, so you don't need to take screenshots of that one. So I hope that the video was helpful in simulating or understanding how to simulate the flexible manipulator and apply terminal sliding mode control on it. Thank you for watching, and we'll see you in the next video.